So, like any function, the trigonometric functions have inverses as well. However, unlike most other functions, the trigonometric functions are periodic. And in order to be inverted, a function has to be one-to-one. The very nature of a periodic function is that it repeats a pattern of y values over a fixed interval. But the very fact that it's repeating them at all, and that it repeats them over and over and over and over again, means that we're going to have some very drastic reductions in the domain. As opposed to something like y equals x squared, the parabola, where we had to cut away half of it, but we got to keep the other half. We're going to have to cut away the vast majority of the trigonometric functions in order to invert them. So, in addition to that, it helps to look at these and to understand what the inputs and outputs are, because they swap between the two functions. Now, first off, let's look at the sine function. So, the domain of the sine function is negative infinity to infinity, and the range is negative 1 to 1. Now, the general rules for restricting domain in order to create an inverse function are that you want to keep the original range. You do not want to lose any y values. You just don't want to repeat them. So we don't want to cut away anything that's going to prevent the function from rising up to positive 1 or down to negative 1. On the other hand, we don't want to be repeating any of them either. Now, one of the other guidelines says that we should keep as large of a portion of the domain as we can. Well, we'll keep as much as we can, but we're going to have to remove an awful lot of this function. Another rule says that when faced with the option of the right or the left, that we should try and keep things that are more towards the right because they correspond more towards a positive value. And this being an unaltered sine function, no transformations or anything, that means that we want to stick to the right of 0 if we can, if we're presented with that option. And lastly, we want to keep, if possible, the central value, which for an unaltered function like this is typically x equals 0. So if we can observe all of those things, let's start with the idea that we want to keep x equals 0. So we want to keep that point. Now that means that we cannot repeat the y value of 0 that goes with it. So that means we cannot repeat that point or that point or that point to either side. So that means that if we're starting with x equals 0, we're not going to be able to get past here. We're not even going to be able to reach that point. We might be able to get close to it, but we'd never actually reach it. And the same thing to the left here. And if we can't reach those points, we certainly can't go past them, which means that some of the domain restriction is going to include the idea that we can't get past an x value of pi. And on the other side, we can't get past an x value of negative pi. Now that's just to start. Something else we need to consider in here is that even with this restriction, we are still repeating some y values, because from 0, we can go up to our, from 0, we can go up to our maximum point, our amplitude there of 1, but we cannot pass that maximum value, because as we know from talking about extrema, that a maximum occurs when you go up, when you increase into it and then decrease out of it. So we cannot, if we've increased into that point, that means we've hit all the y values going up to it. And once we have a maximum, the only place to go from there is back down. But to go back down means we would have to pass all of the y values that we had on the way up. So we're not going to be able to do that. We're going to have to stop at that maximum and say I can't go any further than that. On the other side, it's the same idea. We can get all the way down to -1, but once we hit that minimum, to go any further would be to come back up and hit the same y values on the way up that we hit on the way down. So what we get is that we're going to have to restrict the domain so that we can't go any further to the left than -π/2 and any further to the right than +π/2. So we're going to have to take this regular domain of the function and we're going to have to restrict it to being between -π/2 and +π/2. Now, the range we don't want to change. We want to keep that the same. We don't want to eliminate any y values. We just don't want to repeat them. So, to start with, one of the relationships between a function and its inverse is that all of the characteristics of the inputs and outputs swap, which means that in order to understand the domain of the inverse sine function, we need to take the range of the original sine function. Oh, excuse me. And in order to get the range of the inverse sine function, that has to be the domain under the restriction of the original sine function. Now, as far as the graph goes, the graph has to also swap x and y values. So if the original graph had y values that went from -1 to 1, now we need the x values to go from -1 to 1. And if the x-axis for the original function was set up in intervals of π/2, then we need the y-axis here to go in intervals of π/2. Here we have the endpoint, -π/2, -1. That would have to switch and become -1, -π/2. Likewise, this endpoint, which is at π/2, 1, would have to switch the x and y's and become 1, π/2. In between, the only other nice point we have here is the origin 0, 0, and if we switch 0 and 0, we still get 0 and 0. So the inverse sine function is going to exist between these 2 points on the ends, and in between, we get a function that looks like this, a little bit like a cubic function, but definitely with those 2 endpoints to either side. And that's the entirety of the inverse sine function. Now, what exactly is inverse sine, and what is the notation for it? Well, the exponent, so to speak, of -1 on a function is what we use to indicate an inverse. So up here, this f inverse, it looks like an exponent of -1, but it means inverse. F inverse, and therefore sine inverse. Now, that is an unfortunate notation because, again, as we've already seen with functions, a -1 like that tends to make us think of an exponent. And it's really unfortunate that the notation is really the same as it is for exponents, even though it means something completely different. So there is another notation for inverse sine that I prefer, and I'll get to it in a moment, but to understand what it is, it helps to understand what the inverse sine function is really doing. So it helps to go through this and really understand what are the input and output values of a sine function representing. Well, for any trigonometric function, the inputs are angles in radian measure. Now, the output is different depending on which trigonometric function we're talking about, but the output value of a sine function is a y-coordinate on the unit circle. Now, once again, inputs and outputs switch when we go from function to its inverse. That means that input values here are going to be y-coordinates on the unit circle. And the output value of the inverse sine function will then be an angle in radians. That gives us a way to interpret the sine function, and it actually gives us a way to notate it that doesn't use that annoying -1 exponent kind of thing. And that is arc sine of x. Now, what exactly does that mean? Why arc sine? Well, let's take a look at an example here. Suppose we are given the question or the expression inverse sine of √3/2. Now, we're then asked, what is that equal to? Well, as with exponentials and logarithms, it helps to take the unfamiliar things such as the logarithm and rewrite it in terms of the more familiar exponential. I'm going to suggest that we do that here too, because even though the trigonometric functions are relatively new to us, the inverse functions are even less familiar. So this statement can be rewritten into an equivalent form that the sine of whatever the question mark is equal to √3/2. So that's how we're going to interpret these. This statement here is asking us the sine of what angle is √3/2. Well, we can answer that by going to the unit circle. Now, we don't want the full unit circle. Excuse me. Didn't work as well as I would have thought. We want just this half of it because remember, this is operating under the range -π/2 to +π/2, which means here that's the domain. The angles are restricted to -π/2 to +π/2. The idea is that we want only one such angle. We don't want to have multiple angles producing the same sine value because then the function would not be 1 to 1. So we can create this equivalent statement, sine of what angle is root 3 over 2, but in order to do that, we need to be inside the restriction. And we can use the unit circle. Our knowledge of it to help us realize that the angle here is pi over 3 to get to a point that has a y value of root 3 over 2. And in that way, we can answer this question, that the inverse sine of root 3 over 2 is equal to pi over 3. All right, now what is this arc business about? Well, there's actually an interesting thing about the unit circle, and one of the reasons that we use the unit circle, and that's that not only is the angle measure equal to pi over 3, but the length of this arc is actually also equal to pi over 3. Arc length is usually represented by the letter S. And the thing is on the unit circle, arc length and angle measure are the same thing. In fact, in any circle in general, the length of an arc intercepted by a central angle with measure theta is equal to theta times the radius. So the bigger the radius, the bigger the circle is, the longer the piece of arc will be. But if we stick to a radius of 1, as we have on the unit circle, then the length of the arc is actually equal to the amount of rotation, the angle measure in radians. So another way to write inverse sine then is arc sine, and the interpretation of arc sine is that we are asking what is the length of the arc, and therefore the measure of the angle, whose sine value is root 3 over 2. So I kind of prefer the arc notation for the inverse trigonometric functions because I find the negative 1 looking like an exponent to be very confusing because it does look like an exponent and it makes us think of exponents. But unfortunately it is not. It is inverse. I like the arc sine notation better because it avoids that confusion, and it also actually literally translates into what is the arc length whose sine is root 3 over 2. So it literally kind of reads as, as the question it's asking. What is the length of the arc whose sine is root 3 over 2? Now, each of the other inverse trig functions has an arc notation as well, and they all work in very similar principles, although the domain restrictions are a little bit different. So let's skip over to inverse cosine here. Now, the cosine function is very similar to the sine function, except that it is shifted over a little bit. And then if we're going to stick within the domain restriction guidelines we typically have, that's going to definitely change some things. So like before, what we want to do is we want to keep the center point. We want to keep x equals 0 if we can. Now, x equals 0, that's the location of an extremum here. And what we saw before with the sine function is that we cannot go past an extremum because we can't have both sides of it. If we were to take both sides of this, we would be going down on one side and down on the other, which means we'd be having the same y values on both sides. So we definitely don't want to do that, which means we have a choice. Do we take to the left or to the right? And one of those guidelines says that when you have when you're presented with, hey, I have to choose left or right, that you typically choose right. And we can progress from our high point of positive 1 all the way down to our low point of negative 1 before we have to stop because we hit another extremum and we cannot progress past it. So our restriction is, again, quite expansive. We are eliminating the vast majority of this function. In this case, we are keeping from 0 to pi. Again, the range is then unaltered. To go then to the inverse function, the inverse cosine, our domain here would be -1 to 1, and our range would be 0 to pi. So again, we get that interchange of x and y's, our interchange of domain and range. For the graph of the function, well, our x values have to now take on the y values from the original. So again, we're going to see our x-axis now have tick marks at distances apart of 1. And in the original function, our x values have a spacing of pi over 2. So now our y-axis will have spacings of pi over 2. Our points then, well, our left endpoint up here is 0, 1. So that's going to become 1, 0 in the inverse function. At the other endpoint, we have pi, -1, which is going to become -1, pi. And in between, we have pi over 2, 0, which is going to become 0, pi over 2. In between, then, our function's going to curve like this. And again, that's it. That's the extent of the function. That's all there is. We had to cut the cosine function down to such a tiny little section of the graph that when we invert it, we likewise have a tiny little section of graph, and that's all there is. So again, understanding what the cosine graph, the inverse cosine function is asking us, it helps to understand what the cosine function is doing with its inputs and outputs. So the inputs are, again, angles in radians, and the output values of the cosine function, well, this time we see a difference. The outputs are x coordinates on the unit circle now. Now, that is something that is a little bit odd because the output value we're used to calling a y, and with sine that makes perfect sense because sine gives you the y coordinates. But here, the output value of a cosine function is an x coordinate, which is why I'm writing out the verbalization. I'm writing out the words of what the inputs and outputs are because it really helps to have the full sentence. You don't want to say, oh, outputs are y. No, in this case, outputs, you also don't want to say outputs are x because that's going to be very confusing. You need a full description. The outputs are x coordinates on the unit circle. For sine, the outputs were y coordinates on the unit circle. So it's more than just outputs are x, outputs are y. We need to be a little bit more descriptive here. With the inverse cosine then, first of all, we have the alternative notation arc cosine x, which again is, I think, preferable. Here, the input values, whichever form of it we're using, here the input values are x coordinates on the unit circle. And the output values are our angles in radians. So, much like with the inverse sine, if we are asked a question such as, what is the inverse cosine of negative root 2 over 2, or the alternative, which I prefer, the arc cosine of negative root 2 over 2. Remember then, the arc notation is meant to say, what is the arc length, also known as the angle measure, whose cosine value is negative root 2 over 2. So to rewrite this in terms of the original cosine, we could now say cosine of theta equals negative root 2 over 2. So again, we're asking what is the arc length, or the angle whose cosine is. The cosine of this angle is negative root 2 over 2. Now, remember that we are operating under a different restriction here from the sine function. We are operating under the restriction that we are on 0 to pi. So a different restriction, because now it's x coordinates. We don't want to repeat any x coordinates on the circle. The output value of a cosine function is an x coordinate on the circle. We do not want to repeat any x values. So we want to have all the x values going from -1 up to +1 with none of them repeated. All we have to do then is use our knowledge of the unit circle to say, okay, well, I know that there is a point over here that has an x coordinate of negative root 2 over 2. The only question is, what is the angle measure? Well, the angle measure would have to be 3 pi over 4. So the arc cosine of negative root 2 over 2 is equal to 3 pi over 4. That brings us to the tangent function. Now this is the last of the functions we will be working with the inverses of. The other three, the reciprocal functions, cosecant, secant, and cotangent, do have inverses as well, but for our purposes it will suffice to deal with the original three. Now, oh, there's a typo in there. The domain of the tangent function, which, by the way, should have an equal sign here, there we go, or rather not equal to, x cannot be pi over 2, or any angle that is an integer multiple of pi away from it. Those are where the asymptotes are here. Pi over 2, 3 pi over 2, to the left, negative pi over 2, negative 3 pi over 2. The good news is, though, that looking at the graph, tangent is actually way easier to restrict the domain of than sine and cosine. It's actually pretty obvious. You just have to keep only one of these sections because tangent doesn't repeat itself until you get past an asymptote. So as long as we don't go past an asymptote, we're good. So what we can do is get rid of this piece over here off to the left and all of the other pieces that go further off to the left that aren't shown here, and this piece off to the right. And all we have to do is keep that one little bit in the middle. When we do that, we no longer need to have this big, weird statement, x is not equal to pi over 2 plus n times pi, because that was meant to account for the fact that we have a whole infinite series of asymptotes, which we no longer have. So we can get rid of this, and we can write our restricted domain in a much more compact sense. We stick between negative pi over 2 and positive pi over 2. Now, unlike the sine function's restriction, this is an open interval because we can't actually reach the asymptotes. So we still stay between negative pi over 2 and positive pi over 2, we just don't get to the endpoints. So, once again, for the inverse tangent function, we simply reverse these. Excuse me. For the inverse tangent function, we simply reverse these. The domain of the inverse tangent is now negative infinity to infinity, and the range of the inverse tangent function is negative pi over 2 to positive pi over 2. Oh, that did not go well. Let's try that again. I think I must have highlighted part of the graph by accident. That's better. Okay. So, like before, we're going to take our axes and we have to basically flip them. Our x-axis now is where we should be counting by ones. And our y-axis now is where we need to be counting by pi over 4s. Remember, excuse me. Our y-axis will be where we have to count by pi over 4s. Our asymptotes then are going to be at y equals pi over 2 and at y equals negative pi over 2. In between then, we have to pass through the same 3 points but reversed. So instead of pi over 4 comma 1, we will have 1 comma pi over 4. 0, 0. Well, when that's flipped around, it's still 0, 0. And the other one down here, negative pi over 4 comma negative 1, will become negative 1 comma negative pi over 4. Well, we have to pass through those points and we have to observe our asymptotes. So the inverse tangent function is going to end up looking like this. Like with the other two, we will define inputs and outputs. As always with a trigonometric function, inputs are angles in radians. The output, however, changes depending on which trig function we're talking about. Here we're talking about tangent. So sine tells us the y-coordinate of a point on the circle. Cosine tells us the x-coordinate. Tangent, however, tells us the slope of the terminal side. Therefore, when we come over here and we have inverse tangent, or better yet, arctangent x, the inputs here are slopes of terminal sides of angles. And the output value is the angle. So let's take a look at an example of how to work with this. Suppose we're asked for the inverse tangent of the square root of 3, or the arctangent of the square root of 3. Now, the output of this is going to be an angle. So what this is asking is, what is the arc length or angle measure? Same thing here. Whose tangent value is the square root of 3. And like with the other two inverse functions, it helps to rewrite this into the slightly more familiar form. Tangent of theta equals the square root of 3. Well, once again, we turn to the unit circle. If we know it as well as we should, and by the way, once again, we're looking at a similar restriction to sine, except we can't actually hit those two vertical terminal sides. But still, we can use our knowledge of the unit circle here. The angle whose tangent is square root of 3 is the angle pi over 3. Therefore, the arctangent of the square root of 3 is equal to the angle measure pi over 3.